I'm Eric Cutter, partner at E3, and helped oversee this project, and very excited to have this team presenting today on what was a study ordered by the California Public Utilities Commission for all three utilities in California to assess the impacts of electrification on the distribution grid, including a very granular spatial and temporal forecast of where EVs and heat pumps and electrification is going to occur on the distribution system to help understand the cost drivers and how those costs can be managed. We jump to the agenda slide. I'm going to introduce our speakers today. We're going to start off with Tom Huynh, who's the manager of interconnection modernization analysis at PG&E, along with Bill Peter, who's the manager of integrated grid planning at PG&E. And then Caitlin McCann, who is a managing consultant at E3 and was the project manager for this project, and concluded with Jesse Fallick, vice president at Integral Analytics. So we're going to take questions in written form in the Q&A on the WebEx. I will be monitoring those throughout. If there are any important clarifying questions, we'll cover them at the end of each section. But otherwise, hope to leave plenty of time for a full discussion and Q&A period at the end. And so with that, let me kick it over to Tom.
Hey, good morning or good afternoon. Tom Huynh here. I wanted to dive into the EIS a little bit in terms of the background here. But before I get into the EIS, what I want to sort of frame up is what PG&E is seeing. So let's go to the next slide. So over the next 15 years, right, where PG&E is faced with an opportunity of serving a significant amount of growth that we're going to be seeing over the next 15 years. And what you're seeing on the right is that growth. It contains about 10 times the amount of electric vehicles, 7 times the amount of behind the meter storage as today, and twice the amount of distributed generation. Alongside that, we're going to be seeing a lot of data centers that are mainly connecting to our transmission system, but we have some that are connecting to the distribution system as well. And so when we look at this and we see this growth that we're seeing on the right-hand side, this is an opportunity for PG&E to serve all this electrical load and see what the impacts are on the distribution system. And so how do we sort of plan for this and prepare for this? Well, that's where our EIS came in, or the Electrification Impact Study. And so let's go to the next slide. Our EIS was essentially, as Eric mentioned earlier, is an estimate of our long-term distribution infrastructure cost. And it's associated with achieving sort of California's electrification goals. And we wanted to be able to plan and prepare for that opportunity. So how we did it is we did 3 main scenarios, while including a sensitivity scenario around electric vehicles. But our main 3 scenarios, scenario one being our base case, which is our mitigated scenario. Think of this as how we plan, how we solution, and how we mitigate as of today. So we took engineers, and we used a lot of engineers to really think of all these solutions that range from free cost alternatives, such as free transfers from circuit to circuit, bank to bank, while also thinking of how we could create new substations. And so we thought of low cost alternative solutioning to very high cost within all 3 scenarios. But what I wanted to highlight here is our base case is a mitigated base case. And it was also based off the 2023 IPER, which is our energy forecast that we get from the California Energy Commission. And so that was our base case. Our scenario 2 was a way of us looking at equity. And how we did that is we essentially scaled the amount of DER for our disadvantaged communities. We scaled them upwards to make it the same as our non-disadvantaged communities. So keeping the same adoption as our base, but then scaling the disadvantaged communities higher. For scenario 3, what we did there is we looked at demand flexibility and what demand flexibility could do for some of the distribution infrastructure costs, right? So evaluating what if we manage charging, especially since we're going to be sent 10 times the amount of electric vehicles, how could we manage that charging to not affect the peak load or affect the feeders and banks as much as they would today, right? And so it's looking at that and evaluating the V2Gs or the vehicle to grid, the battery storage, and just introducing more managed charging, not just the time of use rates. What I didn't mention here is that scenario 1 or our base case includes some of that. And so scenario 3 is a scaling up of that, or looking at more of the demand flexibility in our scenario 3. And then scenario, or our sensitivity scenario, is our EV capacity case, where we're looking mainly at how we can scale the electric vehicles a little bit more realistically. What I didn't mention is that we disaggregate a lot of the energy into all the spots of our EV loads. And what that means is that we don't actually get like what that is realistically at that service point or at that location. And so they sort of get spread out in terms of that load, which is not really what we're going to be seeing on the system, more specifically on the secondary and as well as this distribution side. And so we explored that as part of the EIS, but we won't be covering much of that during this presentation, but feel free to go to the report to get more details. So with that, I'll go to the next slide. And as all utilities, or I would say a majority of utilities, we plan for a summer peak. We plan for what the system is going to be, whether that's a summer peak or a winter peak. I guess it just depends on where sort of our topology lands. But for us, we still see a majority of the peak land in the summer. We'll get into a little bit of details in the summer and winter, but we still see the peak in the summer. And what you can see here is that we're seeing sort of our base case land at 21.4 gigawatts in 2025. And we're seeing that increase by 6.4 to 27.8, right? So what that means is that that growth that I mentioned in the very beginning, that growth has not been historically seen. And you can see over the next 15 years, we're going to increase by, about 30 to 40% of that. And so when you think about that opportunity, that's a growth opportunity within the next 15 years of a lot of significant 6.4, right? With the other two scenarios, again, the equity, as we scaled up the amount of DER growth, we're going to see that increase the summer peak. Obviously, because we scaled up the amount of electric vehicles and battery storage within those areas. And that's going to increase the summer peak in 2040 by 1.8 gigawatts. And then for demand flexibility, conversely, we're going to see that shift downwards, right? Which is what we expected. We expect demand flexibility to leverage some of those V2Gs, the electric vehicle, or manage the vehicle charging, so that we're not affecting the summer peak as often. And that's going to bring that downwards of 2.2 gigawatts. And so I haven't talked about cost, but I'm going to hand that over to Bill to talk about the most exciting part of the key takeaways, the cost, as well as the rates, the impact on rates. So Bill, I'll hand it over.
Great, thanks, Tom. So let's go over the results of the study. So in summary, we're talking about a lot of load growth, as what Tom was showing, and a real opportunity here in terms of that load growth and electrification growth. But the investments needed to serve that load growth on the primary and the secondary system totaled between $23 to $32 billion through 2040 for PG&E service territory. And that seems like a big number, but it's a lot of load growth, as we were just showing, is being served here. So a couple things to note about this. This is the primary and the secondary system. I think most of the audience knows what that means, but primary, right, is those poles and wires that are running, down the streets, the feeders. And the secondary systems are like those pole top transformers and maybe those line drops that are running through the house. So the scope of this study really included the full scope of the distribution system, from that distribution substation all the way down to the actual premise. It didn't include, the individual premise, like the panels and things, but the whole primary and secondary system is in the scope of this investment. So if you look at the plot on the right, that's those three different scenarios plotted over time, the amount of investment needed. The blue line is the base case, which has about $25 billion worth of investment. With the equity case, Tom mentioned how we essentially have more load in that case with the more higher EV adoption in the disadvantaged communities. So we see that more infrastructure is needed to support that load, but we also have more load, which actually, as we get into the rates part of this, would offset that. And then on the enhanced demand flexibility scenario, that's shown by the dashed orange line, we see a reduction of about $1.8 billion by the use of that enhanced demand flexibility, that extra demand flexibility on top of the base. So also looking at the right, you'll see that the line doesn't curve up. It's not like we have a big L here with a big dramatic increase in investment. It's actually pretty flat, and if anything, kind of tapers off over time. And so that was encouraging to see. The part of this is that the investment that we make in capacity, we can continue to use that as we see more load come onto the system. And that this investment is a significant ramp up from historical trends for PG&E on capacity, but we've actually been ramping up as we've been seeing this load growth occurring. So it's actually pretty consistent with our current investment rate, to give you some context. Okay, so moving on to the next slide. So if we look at the primary and the secondary components, an important finding in the study is that actually the secondary was the majority of the costs that we found. An important note, and the team will talk about this in detail, is our secondary modeling. We took a novel approach to modeling a secondary system in which we really looked at the geographic nature of the secondary and not just the overloading or the capacity itself of the secondary, but how you would serve new business loads, including like the distance to the transformer and whether or not you'd be more likely to put a new line drop in, for example, versus just to upgrade that equipment. But so the main takeaway here is that the majority of the costs were on the secondary side because of that full scope of the secondary assessment. But let's move on to the next slide. So when we look at what does this mean for our customers? So we did an analysis of what this would mean for distribution rates, all else being equal. And so let me talk through this. So on the right, essentially what we're showing in the top orange bars is the cost element. So that's the revenue requirement. So all these investments we just talked through, that $25 billion worth of investment, that shows up as a revenue requirement in our distribution rates. And as we make those investments, of course, that revenue requirement is going to go up in time. And then at 2040, it starts to depreciate. That's why you see it start to taper off after 2040. Now, the blue is the revenue offset. So that is essentially the extra load growth that we're having. Now they're going to be contributing towards that rate, and that essentially provides a downward pressure on the rates. So that revenue offset is shown in blue. That also grows over time as we bring more load on. Once we get to 2040, of course, that load doesn't just disappear, right? That load's going to continue. So we see that revenue to continue after 2040. That's that flat part on the bottom. And then the red line is the difference between those two. So you can see it's the net RRQ is relatively flat with a small upward pressure on distribution rates, about 1.5%. Then it turns negative after 2032 and actually reaches about a downward pressure on distribution rates of 25% by 2040. So a couple things to note here. We're just looking at distribution costs and just looking at distribution revenues. So we're not looking at transmission cost side, but we're also not looking at transmission revenues. Same thing with generation. We're not looking at that. This is just the distribution side. The other side, part of this is we're only looking at the capacity investment. So if you had this load growth, you might expect you also need to make investments in reliability or wildfire safety. So this is just the capacity portion of the investments and the load growth that we see. And of course, it's just the incremental as well. We're not considering any of the existing, use of the grid. But certainly, there's an opportunity here, right, from all this load growth to achieve a downward rate pressure. We see this in all three of the scenarios, a downward rate pressure on distribution rates in all three scenarios. And really the key driver here that we really want to stress is it's this electrification load growth. That's what really drives this opportunity. Okay, so moving on to the next slide. So just to recap some of the key strategic findings before I turn it over. So first we had investments. We were able to estimate the investments through 2040 for a large electrification growth of about 23 billion to 32 billion by 2040. And then one thing we touched on briefly, Tom mentioned how that base scenario includes mitigation and includes engineering and includes load transfers. We actually found that that work saved about $3.4 billion in primary savings through 2040. So in other words, this isn't just an analytical, put the numbers in and let it run. We actually used a lot of engineering. We found that engineering really matters in actually making sure you have a robust plan. And there was no high cost scenario here. All the scenarios were mitigated. We touched on the new approach to long-term secondary planning that the team will build on the next slides, as well as we'll dive in deeper on what enhanced demand flexibility, and in particular, how orchestration was key to achieving those savings. Well, finally, I covered how this electrification is really an opportunity, right, to provide downward rate pressure if done right, and if we can actually achieve that load growth on the system. Okay, so with that, I will hand it on to Caitlin from E3. Thanks.
Thanks, Bill. So next, we will talk about the analytical methods for this work. This slide introduces the overall methodology that we used in the EIS. At a high level, the study follows this three-step framework that connects electrification adoption to the distribution system impacts and costs. So first, on the left, we model where electrification and DER adoption is likely to occur using E3's Forecasting Anywhere tool. This step also leverages the California Energy Commission's IPER adoption forecast and translates it into location-specific adoption across PG&E's territory. Second, in the middle, we translate that adoption into hourly load impacts using detailed load shapes for each technologies, such as electric vehicles, building electrification, storage, and others. And third, on the right, we allocate the adoption forecast throughout PG&E's territory at a granular level, and then simulate those load impacts on the distribution system, identifying overloads and applying engineering solutions to estimate the costs. And this step is using distribution planning tools such as SIME and LoadSeer. So on this slide, we'll get into the tools used. So we start with E3's Forecasting Anywhere in the blue box on the left, which generates scenario-based inputs used in this workflow, such as technical potential and propensities for each technology. And essentially what that means is where customers can adopt technologies at a granular level, and then also where they're likely to adopt technologies in areas where there is technical potential. In the green box, another key input to this study are the hourly technology specific load shapes. And then all of those data sets are then passed into LoadSeer in the center in yellow, which is the distribution planning tool used by PG&E and built by Integral Analytics. And then LoadSeer allocates that adoption forecast spatially and then applies the load shapes to model impacts down to the secondary level. And finally, in red on the right, SIME is used for detailed power flow modeling by the distribution engineers at PG&E, as well as applying the solutioning at the feeder level. So overall, these tools allow us to go from the high level adoption forecast all the way down to this specific system constraints and resulting costs on the right. Here we zoom in on how Forecasting Anywhere and LoadSeer work together. So Forecasting Anywhere calculates both the maximum possible adoption, which is the technical potential, as well as the likelihood of adoption of all these different technologies that we're modeling, or the propensity at each location that we're modeling. And then LoadSeer takes that information and allocates the adoption forecast geographically to granular locations across their territory. as well as applying the detailed load shapes for each technology. So the result is a highly granular view of how electrification evolves over time, not just how much load grows, but exactly where and when it shows up on the system. So on the right, this is just a visual of that. One of the example outputs from the study where we're showing the geospatial adoption of residential EV chargers over time throughout the study period. Next, we'll go into the load flexibility part of this analysis. So this slide introduces the enhanced demand flexibility scenario and the incremental flexible loads we modeled. So as Bill mentioned, this scenario is modeled as a comparison to the base scenario to study the possible cost savings from load flexibility. The base scenario does model business as usual flexibility, including managed EV charging to time of use rates. And the load shapes used are partially based on PG&E AMI data, just to make sure it's reflecting current trends in the business as usual or base scenario. And this enhanced demand flexibility scenario uses the same underlying adoption as the base case, but applies these additional load management strategies that we'll go through. So for EVs in green, this included increased participation in managed charging, more actively managed optimization, charge management optimized to feeder specific needs, which we found to be important, as well as vehicle to grid or V2G. For building electrification in the light blue, this included shed and shift demand response. And for battery storage in purple, again, this is incremental to what was modeled in the base scenario. So we modeled increased behind the meter battery storage utilization from the base scenario. And these assumptions are all benchmarked to the California Energy Commission's DFLEX toolkit. And the goal is to represent a more advanced level of load flexibility than today's baseline. So the chart on the right, we're showing the coincident peak demand flexibility. This chart illustrates how load flexibility modeled in this scenario increases over time. So 2030 on the bottom up to 2040 on the top. By 2040, we can see that the total flexibility reaches about 2.7 gigawatts at the system peak. And EV flexibility, those two green components of that bar become one of the largest contributors to peak reduction, reducing the coincident peak by about 1.8 gigawatts by 2040. This slide highlights one of the overarching findings from this part of the analysis, that flexibility has the greatest infrastructure value when it's coordinated with local grid constraints. So in this study, PG&E tested an enhanced demand flexibility scenario with orchestration, as well as the sensitivity without orchestration, which this slide is comparing them. The non-orchestrated case still reduced the overall system peak, but it did not account for local constraints on the distribution system, such as secondary transformer loading. And as a result, it did not reduce long-term distribution infrastructure costs. And orchestration in the context of this EIS analysis refers to the ability to manage the electric load in response to local grid constraints in a manner that can be relied upon for planning purposes using firm dispatchable load management. So even though load may be managed to the system needs or at the substation bank level, for example, you might still be triggering an upgrade on some of the feeders it serves. So the results show that the orchestrated case reduces total distribution infrastructure costs by about 1.8 billion or 7% by 2040. By contrast, in the bottom row, the non-orchestrated case reduced costs by only 0.5%. So the key takeaway is that demand flexibility can be valuable, but the value does depend on being locally informed and reliable for planning purposes. So on this slide shows how electrification changes the timing of peaks and why that matters for planning. In this chart, we are sorting PG&E banks by their peak period, with summer peaking on the left and winter peaking on the right. 2025 is shown in light blue, and 2040 in dark blue. So as you can see on the far left, about 67% of PG&E's banks have the same peak period as the CAISO system, which is the summer evening. And we can see how this changes over time. So as electrification increases, that alignment starts to break down. By 2040, the share of banks peaking at the same time as the distribution or as the CAISO system drops to about 51%, which represents about 16% decrease. And peaks are spreading into other times of the day, as well as to winter. We observe the shift towards winter peaking as well, driven largely by building electrification. By 2040, around 37% of banks are winter peaking, which is about 20% increase from the 2025 numbers. So here are the key takeaways: that the distribution constraints are becoming more localized and less aligned with the bulk system peak. And that's important because it means that system level solutions alone aren't enough. The system will increasingly need planning approaches and load flexibility approaches that are targeted to local conditions. Last slide in this load flexibility section. This slide introduces load factor, which is an important metric for distribution planning. It is calculated as the average demand over the peak demand. And the study finds that the average feeder load factor is around 70% and doesn't change dramatically over time in the base scenario, but it does in the enhanced demand flexibility scenario. With flexible load, the load becomes more evenly distributed throughout the day, so the load factor increases. And this is seen in the chart here, which plots the number of PG&E feeders on the y-axis by their load factor on the x-axis. The 2040 enhanced demand flexibility scenario results are in the darker green bars, and the 2040 base scenario are in the light green. And as you can see, in the range above 70% load factor, so the far right of this chart, that's the range where thermal ratings on the equipment may need to be adjusted down. And you can see that there are more feeders in that part of the chart in the enhanced demand flexibility scenario. So high load factor can be beneficial in some ways, but it also has implications for equipment ratings as well as operational flexibility, because the higher load factors mean that the equipment runs closer to its limits for longer periods, which can reduce the thermal capacity and flexibility for operations. So just a trade-off, something to keep in mind. Flexibility reduces peaks, but it also changes how assets are used. So something to keep in mind for distribution planning. And next, we'll go into secondary distribution system modeling, and I'll pass it over to Jesse from Integral Analytics.
Thank you, Caitlin. So let's start off and talk a little bit about, as far as our secondary cost analysis were concerned, the overall goal, which was really to develop this granular and transparent estimate of secondary distribution system costs across all of the AI scenarios, and specifically aligned with PG&E's distribution planning standards and several of their assumptions. There were a lot of challenges that we encountered and that have been encountered before that we tried to surmount in this analysis. One, across all utilities that we've worked with, secondary distribution systems are often less comprehensively modeled. There's less data available than primary systems. Even with great data, for a study of this magnitude, detailed engineering level solutioning like was done for the primary system in this study is typically impractical. And something that we'll talk about a lot, and that Bill mentioned already, many forecasted new loads occur beyond the service radius of existing secondary assets. So the model has to be able to install new transformers and secondary equipment where needed. And that additional capacity that's installed needs to be preserved and it needs to be utilized throughout the forecast horizon. So we can move to the next slide. This is a little bit of a review of what Bill said, so I'll go through it quickly. In the base scenario, we estimated, in terms of overall results, we estimated total secondary top costs to be almost 16 billion over the 15-year forecast horizon. And as you can see, as expected, costs for the equity scenario were higher, and for demand flex were a bit lower. I think the two really important metrics here to take note of, that the secondary costs represented 62%, more than half, as Bill mentioned, of the projected distribution costs, and 78% of those costs were new service transformers, new secondary equipment versus replacements. And from my perspective and the perspective of the folks that worked on this study, this really points to the importance of accounting for spatially isolated loads that cannot be tied into existing service transformers. You can go to the next slide. So as I mentioned already, the analysis took into account real distribution planning standards and assumptions. These were things such as the maximum tie-in distance, standard transformer sizes, as well as the policy around sizing up to meet future loads, and also the max loading allowed before replacement. PG&E was very interested in how overall costs would change when these assumptions were changed, so we did perform a sensitivity analysis on a number of the inputs. And so you can see here how, for instance, a policy to simply install one standard size higher than what is technically required in the model actually can reduce the projection of overall costs by over $1 billion or more, depending on the forecast scenario. You can go to the next slide. Okay, so let's get into some details on the method, which in my experience is a lot easier to understand visually. So we have a visual here. So the model steps through annual loads spatially, one at a time, and determines what the existing secondary transformer capacity is within this predefined radius. And then it allocates summer and winter coincident load proportionally to the existing transformers up to that defined maximum loading I mentioned before. And transformers are then replaced to accommodate the load, and that's subject to that size up policy that I also mentioned earlier. And adding to that other secondary costs like line extensions that are required. I guess, importantly, if there are no existing transformers in the search radius, we build new secondary capacity to accommodate the load. And also important, as I mentioned, built or replaced capacity that we have here is immediately available in the next year for additional surrounding load growth and for the full 15 years of the forecast horizon. And we do all of this, which is sort of depicted here visually, but we do all this through a spatial indexing system called H3 indexing, versus being tied too closely to the existing grid. And so this allows us to ensure we're taking into account the real costs of these spatially isolated loads. You can go to the next slide. And can you just click through this just to show everything? Because I think there's some, yeah. So this is just stepping through what's actually happening, stepping through the method I just described. And so in this actual example, you can see there's coincident load in this center hexagon we're showing here. 1.9 kVA of new coincident summer load representing 2.5 kVA of new coincident winter load, and what's happening is that new load is being allocated to the eligible transformers. You can see there are 2 transformers that are outside that predefined assumed radius, tie-in radius, that are not getting allocated to. And even though there's some load being allocated to existing transformer capacity, one of those transformers is replaced to accommodate the incremental load that can't be allocated. And then according to this size up policy that's in place, a 100 kVA transformer ends up being installed. And all of this is detailed here. I saw some in the questions. I was just skimming through the Q&A. I saw a question related to validation. And the goal of the validation that we did was basically to ensure that all of the assumptions and inputs were being taken into account that PG&E had, and all of those are I think were detailed in the model, in the report. And so the goal of the validation was to make sure the model was working correctly and taking into account all of the assumptions that PG&E had provided. And so what we produced was basically for every single one of these half-acre hexagons and every single annual coincident load, we provided kind of an extract that stepped through everything that was happening. And as you can see here, so how many transformers were found, what was the total existing capacity, how much additional capacity was there needed, what was built, whether there was size up policy in place. And so that was kind of the extent of the validation and how we stepped through that. So it's very similar to what you see here, just for 1 million or so hexagons. And that is pretty much it. I think that's the last slide in my section. I can hand it back to Bill to wrap us up.
Okay, thanks. So just to recap, to bring it back up to a higher level of what the study findings were, as we said, we found between $23 and $32 billion in distribution investment through 2040. I actually saw a question about this. One of the big benefits of this study for us, for PG&E, is we worked with our vendors who helped us build these capabilities directly into our planning process. So this wasn't just a study for us. This was also a way to start developing this capability. That's true of scenario planning. That's true of our first time really trying to do a long-term secondary planning study like this. So we learned a lot. We also, in terms of our load shapes, in terms of modeling demand flexibility, all these things, we took the approach of working with our partners to develop these tools, these shapes, these capabilities so that we can leverage them in our future plans. And so a lot of that is we're planning to roll out in the coming years, starting, scenario planning, et cetera. But we also know that, electrification growth is coming, right, as is demand flexibility. So, it was really appreciative of this chance to be able to build this capability through this study. The other part is that, I think it often gets overlooked, but the distribution engineering, right, we definitely tried not to just take an analytical approach and really take a mitigated approach and try to determine, start with our base of what we think represents how we actually plan our system. And so, as I said before, that $3.4 billion in savings. But then there's also this extra opportunity, right, of this enhanced demand flexibility, of with orchestration, that we can get that $1.8 billion in savings. So we're learning, we're also really trying to dive in now into how could we orchestrate that to make sure we actually see that savings. And then just to close out, to this opportunity here with low growth, we see this real potential to drive down our distribution rates, which is a huge focus for us right now in terms of affordability. So we're very excited about the opportunity for this high electrification future. So I'm excited to see we have some questions too, and I think Eric, you're going to moderate that. So maybe I'll turn it over to you, Eric, to moderate the questions.
Yeah, terrific. So people have been writing questions, which we as the panelists can see. I think we'll try and organize them and go down in order. There's also, if you would prefer to ask your question verbally at this point, I think there's a way to indicate that by raising your hand and we can unmute you. So starting with, and Tom has jumped in here, but I guess I'll try and go in order, starting with PG&E and Tom and Bill. So Tom, you addressed this, but there was a question on, we're looking pretty far out into the future, and if you had any thoughts about which of these load types, be it EVs or heat pumps or data centers, are the most uncertain or have the largest error bars, and how that might impact the, what you consider a no regrets distribution planning process for that kind of load.
Yeah, I think in terms of, we didn't talk about this much, but as we sort of mentioned in the base case, it includes, as well as the other scenarios, it's based off the 2023 IPER, which is driven by California Energy Commission. And so the energy forecast that we were given, to the best extent, they used and deployed a lot of resources to figure that amount of energy for each utility, right? And so what I would say is it based off the policies that were in play in 2023, that's the amount of growth that was depicted for each load type, right? Now since 2023, there has been some policy changes that have impacted some of those things, right? Such as EVs. And so, yes, the EV may have a quote unquote maybe like a bigger error right now, but from what we're seeing. But I think in terms of what we in sort of a grander picture is that EV growth will eventually occur. It just may not occur at the time period where we see these things. And that's true for a lot of things that we see within PG&E. And I know LoadSeer has their own opinion about load growth as well, but it's just about timing. Like we will see the load growth and we know the demand will eventually trend that way. We just don't know timing because of some of these policies that can affect these things.
Great. Let's see, looking through, Rajiv had a question about, we looking at using existing grid capacity and how we can utilize that by reducing demand. And that, I would say, is taken into account directly in the analysis, in that we're looking at the incremental load that is driving identified grid needs and LoadSeer. So to the extent there's already headroom and load management reduces the peak, that would be accounted for in the study. There were a couple questions on how this might influence transmission planning at the CAISO, and we should say, A, we were very focused on the distribution system, and B, be very cautious about trying to extrapolate to the transmission system, both because even though we're showing a diversity of peaks on the distribution, like how that rolls up into sub-transmission, we didn't really look at. And of course, we didn't look at all the data center load that is expected to be coming on at the transmission level. So I'd be cautious about trying to make any conclusions based on this study about what might happen on the transmission system. I think Bill addressed, how PG&E was looking to use this study and incorporate all the learnings for how they do their distribution planning, which will impact their future asks in general rate cases and operational planning. Guess at this point, I'm kind of going down the list. So now we're getting into some questions on the secondary planning. So Tom or Jesse might be able to jump on these. Was any analysis done to check the, and I hope this isn't too technical, to check the allocation of secondary capacity across the different service transformers, or do a single transformer, in terms of finding potential savings? And is it possible that analytical methods are overestimating? So hopefully that makes sense to you, Jesse.
Yeah, I mean, just high level, I think the question is really here asking about mitigations and kind of analogous to the modeling the primary and the cost modeling the primary. Obviously, across millions of service transformers, you can't do kind of this custom mitigation approach, but I think this was done primarily in the way that it was done. It was done through the sensitivity analysis that I discussed, right? So this idea of looking at when we change the assumptions going in, for instance, if we install larger transformers, or if the standard sizes are higher, or if we have a higher max loading fraction, how does that impact the overall cost, right? And that the idea there was to look at mitigations, right? So what could we do? How could we stretch the distribution planning assumptions to look at whether there was cost mitigation there? So that I think that's kind of how I would answer that question.
I
Yeah,
think
I'll add it.
Oh, go ahead, Bill. Yeah.
Yeah, I was going to add a few things. So I think it's a great question. I mean, obviously, with the purpose of this study was to try to get aggregated results on the secondary, right? So we're not claiming that we can forecast, where there's going to be a secondary transformer in 15 years if needed. But another important thing to remember, though, is that like most utilities, right, we don't have like a perfect data set of our secondary system. So I think taking this type of geographic hexagonal approach really allowed us to model. We want to get there, that our model is perfect and we can say exactly, on a forecast that we can mitigate and then say, should we replace it with this size transformer or this, and do an engineering of each secondary. But that's going to be a big effort for us to get to that point. So like most utilities, I think that taking an approach that isn't so based upon just the loading of what you have in your model of your secondary transformers, and instead saying what you're going to have, how we're going to serve this load growth, is essentially the approach we took here. And we did consider, as I said, transformer sizes too, right? So we didn't just take like the next transformers, that's part of the sensitivity, right? To say maybe we should just put one big transformer in and try to serve more areas. Let me add, there's a lot of questions on the secondary, which I totally understand. I'll just add one other thing is, we did try to understand how we actually are doing our secondary system in practice, right? So a lot of this is informed by talking to how service planning is occurring. And the reality is that most of our secondary transformers and line drops, we're not doing based upon loading, like looking and seeing or forecasting load growth on those. We're doing it through the actual new business connections. Now, sometimes those are new business connections that are totally new and far away, right? But sometimes they're new business connections that are essentially still located within a neighborhood or something, but the topography of how you're currently serving that neighborhood, it makes more sense to put in a new service rather than try to keep leveraging the existing services. So we think but we do think it's a learning space for us. I'll acknowledge that. But we did try to really base it upon how we are actually doing the investments in practice now. And the results seem to be pretty consistent with those trends that we see. And then Tom, I think you were going to add something here too.
Yeah, I'll just add one thing. Thanks, Bill. You covered a lot of what I was going to say, but I think in terms of the hexagon placement too, as well as like our standards, what we looked in terms of our engineering standards of how we try to reduce voltage drop on the secondary and how long we can run the cable or under overhead line over to a house or residential or commercial customer, right? Those were in play. And so as we're exploring the size of the hexagon, it really came down to what still fits logically within our standard and what still fits into like a realistic play. So as we went through this cycle of understanding, hey, here's what the numbers look like as you explore just one hexagon itself, it looked very different as if we were to expand that hexagon and say, what if we looked at and explored its neighbor hexagon? And would that still be incorporating of what we do standard with within PG&E. And so those things were things that we were always incorporating, always, cycling through in terms of thoughts and how we were running the analysis there. So.
Great. I'm noticing there are a couple of hands raised. So I'm going to get to those. First, there were a couple of technical questions. Jesse, I think these would be for you, though others feel free to jump in. Of what was the advantage of using H3 indexing over, lat long position and the search radius? And how do we deal with this very data and compute heavy study, and how did that present a problem, or how was that managed?
Those are great questions. I mean, I'll answer them briefly. Those are related questions. When we looked at how we were going to approach this study, and this just aligned with our overall kind of architecture and design loads here. You could absolutely do the same study just using lat longs. It would be extremely difficult to run the compute. It would take a really long time, and it wouldn't have allowed us to iterate as we did and perform kind of the sensitivity analyses that we did. I think the key feature of H3 indexing is the ability to, so for instance, say for a given load or set of loads inside of one hexagon, where are eligible transformers that reflect existing capacity that we can leverage around that load. H3 provides a really fast way to do that. Trying to get the same answer with lat longs and distances would require just billions of more calculations. So it's really a shortcut that allows you to get to the same aggregate answer. And that's kind of the benefit of H3. Yeah, I think that's it.
Perfect. Great. So I'm going to, there's lots of other good questions, but I'm going to move to Rajiv Dabir. So I'm going to unmute, which then I think you also have to unmute yourself, and then you can ask your questions. And next up is Leo Steinmetz.
Yeah, no, thank you. Can everybody hear me?
Yep.
All right, thank you. Yeah, thank you for the presentation. Really good information here. And Jesse might have answered my question. The way, we're at the CEC, at least thinking about this is, and I think Tom alluded to this, there's a lot of uncertainty in how the demand will come, although it seems to be that there's some certainty that demand will eventually come. But is the strategy to maybe look at a scenario where there is, minimal or no demand, and with existing demand, you're utilizing the grid to its maximum capacity? In other words, you are doing all the load flexibility strategies you're talking about, and that creates that extra sort of capacity, and maybe that's not the right word there. And at a minimum, it allows you to defer investments in the distribution upgrades till you start seeing some notable sort of change in demand. So I don't know if that's how it just seemed like you are looking at increased load, and then you're looking at how to be flexible with that increased load. And so my question is, if you don't look at the increased load and just look at the current load, that might help also create sort of, deferment of investments till you actually see how this load is going to pan out. And eventually that might reduce sort of the investment and then the bills, and with affordability being sort of front and center right now. So just want to see how the panel's thinking about that.
Mm-hmm. I see both Tom and Jesse nodding their heads, so we'll toss it, or sorry, Bill. And
Jesse, I want to take a first stab at this. So first, I think that the primary purpose of the high electrification, this study, is to try to assess the cost for a high electrification future. So the idea is we're looking really far out in time, and we're looking at electrification growth and trying to determine what would it mean for the grid. Now, that's especially in the near term, right? How that actually plays out is pretty different. And so, we have our distribution planning process, which is a lot more actually driven by the actual customer demands that we're seeing. So in terms of actual customers submitting their applications, actual communities telling us that they have these specific plans and specific load growth. So it's much more of a, serving our customers and building the capacity to serve them at the at the timelines and at the locations that they need. Now, of course, when you're talking about a study like this, right? You don't have that information about 2040. So I just really want to distinguish between those two kind of approaches. This is more of a study of a long-term cost estimate. And so if you could say okay, if maybe that load growth we see from actual customers doesn't come as fast here, it just may mean that curve we have, for example, could change its shape a little bit, that cost curve we had. But essentially this study is trying to look at a future state where we have electrified a large portion of our economy. That's really what we're trying to represent in the study. In terms of planning, yes, we want to make sure that, when we talk to customers that we're actually meeting their plans and that is the load growth that they actually need, that we're trying to serve. But a lot of these investments, are on the distribution grid. You can do it specific to the actual customers. We have a pending loads and a known loads framework to try to really drive that. Anything else team wants to add on this question?
Great. Well, let me try see if we can squeeze in one more from Leo. I'm going to unmute you, and then we'll wrap up as we're heading to the end of the hour.
Great. Thanks so much. Can you hear me?
Yep.
Great. So this is Leo Steinmetz from the Public Advocate's Office. I have a question about the secondary modeling, but it might actually be more about the forecast underlying it than the allocation modeling, which is just, I'm trying to understand what all of this load outside existing service transformers is supposed to represent. When I think about electrification, I think about small concentrated new loads like data centers and EV charging stations, and then a lot of load on existing service transformers through building electrification and EVs. And so when this study finds a huge number of service transformers that are in new places, I have a lot of trouble imagining, what does that actually represent? Who are those customers? Why are there so many of them? And why do they all need new service transformers instead of being within the range of existing service transformers?
I'm happy to take a stab at that, just at a high level. Bill, Tom, Caitlin, feel free to jump in. When you're doing long-term forecasting, and this is true across, this is something that we focus on at IA and Loads here, is there's a fair amount of forecasted load comes in the form of land use growth, right? So there is significant land use growth projected over a 15-year period outside of current development. That's new development, right? So that's one big piece. Another big piece, areas where there are development, but things like EV charging that you might see in workplace or in highway or public EV that may not be, even though there's development surrounding it, there are, for instance, parking lots and areas where EV is forecasted that does not have an existing service transformer within that reasonable tie-in distance. Those are two big categories that we saw in the context of this study.
Yeah. I'll add that, as I sort of mentioned earlier, is that when we look at the standard of how long we could run the secondary cable, right, we have to sort of meet certain criteria that allow us to ensure that when we serve a customer, we're not serving them, in violation of some of our standards, our voltage standards, for example, right? And so, like Jesse had mentioned, in terms of evaluating some of the land usage, there's going to be new residential customers, new commercial customers, new charging locations. Those are all locations that we would potentially install new transformers. And so whether they're new land or existing land, it could still very well be that we install a transformer. You know, as I mentioned, when we looked at the hexagon level, if we looked at one hexagon itself, 1/2 acre, that really doesn't take up a whole lot of space, right? And so when you look at the commercials, if you lay a hexagon over a commercial property, it doesn't actually take up a whole lot of space on that. And so that's why we expanded a little bit to look at the neighbor hexagons. And that's going to give a little bit more flexibility of like, here's where you could go a little bit outside, you know, a little beyond 300 feet to really see if there's any transformers that could incorporate it. And when there wasn't, that's when it's like, that's when we would install a new transformer. And that's potentially the case, right? If a commercial customer wants to install electric vehicles, we got to put in a transformer that meets our standard and fairly close by to that charging location.
All right. Well, I'm going to wrap us up. Thank you all for participating, the good questions, and we certainly enjoyed presenting these results to you and hope you found them useful. And I think that's it. We'll close it up and have a good rest of your day.